Very well. Who is important among these two? This is Rick's contribution. This is Rick, Professor Trabino and his wife. Who is more important to ultra fast science or mankind? Okay, when I asked who is more important, I did not mean Rick versus Linda. I meant intensity profile versus phase profile. Okay, the intensity profile of a pulse is I of t. The phase profile, let us say in time domain, R is phi of t. How do we figure out which of among these two characters, which you can call the yin and yang of the world of pulses, if you know what I mean, right? They are complementary aspects, which sounds philosophical maybe, but for those who identify with that, it is a good analogy. But which is the more, who is bigger, right? Or who is more important for the society of pulses, right? So, we can say knowledge or wealth, for example. It is always kind of debates, but anyway, before I trivialize it too much, the point is we can set this question up for a practical, experiment, if you wish, a numerical experiment, and find out the following. How do we do that, right? So, this is an original photograph. These two are original photographs of the gentleman and the lady, right. Now, we can do the following. So, this is a 2D pulse or a signal. A photograph is a 2D signal, agreed. Of course, the fact that it has amplitude, it is an amplitude signal seems fairly clear, right. But we can ask, where does the phase come from in just a photograph? We can always ask that question, right. But even if we had an amplitude signal of whatever sort, we should we consider fields here? Let me just call this, each pixel on the xy takes a value f times x, f of xy, right. So, we can Fourier transform this and produce f tilde of, we need two variables. If it is spatial domain, what would it be? Had this been f of t and Fourier transform f of t, you would have said, oh, this should be omega or nu time frequency. So, what should be the Fourier domain variables for x and y? Yeah, so it should be a k corresponding to each of these. Yeah, a k corresponding to each of these. So, now for this two dimensional signal, right, we would indeed have an amplitude. If I now think of this, each photograph being formed, okay, in this case by the Fourier transform of these guys, then we are going to have the following. So, f of x y would be the inverse Fourier transform of this function f, which is a function of k x k y. Now, once again, what is f of f tilde? Oh, sorry, I am missing two factors here. Let me write it like that, e to the power minus I k y y, e to the power minus I k x x. f tilde of kx ky, right? You get that? Of course you do. So, one can view this function f of x y as weighting each, assigning a weight factor for each value of kx and ky. And if we don't subscribe to anything else, we can once again Taylor expand this, right? But then it would be something like a two-dimensional Taylor expansion, one for the x. So, we would have an f naught x, we would have an f naught y, f1 x, and I should have, which would be the derivative, partial derivative with respect to x, x minus x naught, x naught could be 0 and so on and so forth. But we would essentially have this kind of a Taylor expansion plus y terms and so on. So, we can think about it, but okay, the point I am trying to oh sorry, why am I expanding in terms of x? So bad, so bad, so bad. I apologize for this error. So, I should expand this in terms of 0 of kx, 0 of ky, then I should have kx minus, okay, let me just put it as kx, let me expand everything about 0 frequency, which is the DC term and so on, right, kx square and so on and so forth. The point being that I can view this function as something weighting each of these frequencies in the spatial domain, as well as having quadratic terms in the process for the same. I can systematically expand this out, but the point here is the following, that this signal is composed of amplitude as well as a phase term. When I look at the spatial signal as summing up some constituent frequencies from the spatial frequency domain. Spatial frequencies are again nothing but sinusoids of various frequencies in either direction. So, you can think of sinusoids, right, various sinusoids constituting this sort of picture, okay, and all of them adding up, the sinusoids of varying frequencies constituting this and adding up to form such a picture. That is the 2D Fourier transform for you, right. So, well, here is the point we are trying to make. If I now have, okay, since f tilde is a complex function, I would of course have f tilde and e to the I some phi kx ky, okay, e to the phi in the k domain. So, we have two functions that contribute to the reconstruction of this image from the k space to the xy space, that is the kx ky space to the xy space, just like in the case of the pulse, right. It is analogous to, in a photograph, every pixel you have RGB values. So, RG and B are adding up to give you a particular color. So, in terms of color, we have decomposed it into three functions, three eigen functions, RGB, or in certain newer printers you have CMYK. I have a printer like that, right. So, there we use a basis of 4 color functions. Other case we have a basis of 3 color functions. You produce any color by adding, and I mean putting dots in terms of a printer. You mix appropriate amounts of ink and then produce a color in this case. But in terms of LED screens like what we have, LED or whatever display technology, the screens we have, it is 3 colors, RG and B coming to produce a composite color which we perceive, right. So, that is the Fourier space of the color, right. So, likewise a phase function is essentially sort of giving us the relative phase differences, okay. A map of it is a map of relative phase differences, you can see, and we have amplitude also, the amplitude function also playing an equal role, okay. But then it is a teaser to ask which is of relatively greater importance. Now, how do we find out that? We can sort of play this game. Let us say we took these two pictures, we Fourier transformed this, we got then the spectral amplitude and the spectral phase map, all right. Now, what you can do is you retain the amplitude of Rix, that is the male picture, but use the frequency map from Linda's and then do the reconstruction. So, you have f tilde Rick, f tilde you had, and you had e to the I phi Rick, e to the I phi L. Now, do inverse Fourier transform, you should get this picture. But what if we did the following? We took amplitude Rick, because it is signal processed on a computer, make the intentional error of using Linda's phase portrait or phase map, and vice versa. Here you take Linda's amplitude function, okay, there should be moduli to denote that it is the amplitude function, and use Rick's phase map and perform the inverse Fourier transform, okay, I do not know if that is legible enough, and perform the inverse Fourier transform. So, let us see the result of this phase swapping while retaining the amplitudes as they are. Wait. No, sorry, I totally messed it up. I am very sorry, I totally messed it up. Okay, I take everything back. This is correct up to this point, I am correct. Okay, so this is these two, I am sorry, these two are the initial signals which are 2D. Okay, I lost my plot a bit, so be it. What we are going to see here is you retain Rick's phase map, we use Linda's amplitude function, okay. We use Rick's phase map, Linda's amplitude function, and inverse Fourier transform here. On this side we have the phase is true, correct, but we do amplitude swapping, not phase swapping, and what we see here is the inverse Fourier transform. Right. So, let us look at the results. Okay, my writing is obscuring things, so I will erase that. But you see, this left portrait has the lady's amplitude, but still the hat and stuff are visible. Hat, even the thin features like spectacles are visible. And here on the right, it is the face belongs to the lady, but the amplitude comes from the photograph of the gentleman, and you still see features being retained. Of course, we lost some information, some clarity and stuff like that, but this is surprising, isn't it? We thought amplitude is everything, like, oh, I am perceiving. I thought the touch and feel, if you wish, comes from an amplitude. In a statue, there is, you can say, three-dimensional statue, we think no phase, it is just touch and feel, amplitudes, no, statues cannot interfere, there are no phase components. But if you see in the case of this is just a digital photograph, this amplitude swapped reconstruction still seems to retain this information. So, what matters, it seems, for signals, okay, the clear winner, it seems, is phase. Phase always wins. So, now we must ask ourselves the question, if we have a pulse and we want to do metrology, we want to measure the characteristics of a pulse, we can in some sense think of, with a little bit of imagination, think of methods to figure out the amplitude of the pulse. Okay. For example, you say square pulse amplitude, what do we seem to connote? The amplitude of the pulse. Triangular pulse, sawtooth, these are all amplitudes. We are very habituated to thinking about the vital statistics of a pulse in terms of its amplitude. Whereas, what really matters is the phase content. So, measuring a pulse as a consequence and characterizing it should mean a measurement of the spectral phase, because we can't easily directly measure the temporal phase. If we do a measurement in the spectral domain, it should be a measurement of the spectral phase. It should lead to a measurement of the spectral phase, right? That is what we should demand. Whereas, amplitude is, of course, maybe amplitude is a next order term, the thing of next order to also have, so that we understand the total composition of the pulse in its entirety, we obtain its total composition in its entirety, right. So, phase is, that is why we asked in one of the earlier assignments, what is more important, and of course, it was with some foresight, maybe it was just a memory jog that we asked you about, and the answer that we gave in the assignment was phase is everything. But of course, that is more a slogan than a quantitative physics term, but almost everything, it is very important. So, we should therefore keep this etched in our minds, that measuring the phase profile is very important. And we do metrology, which is what we will discuss next about measuring pulses. We have to figure out ways to measure the phase portrait, the phase profile. Now, but of course, it is not obvious how to do this. Okay, how do we measure phase? I already asked you a question earlier about the zeroth order phase. How do you measure that? How do you get a metric? How do we get a metric for this? Except in a clock, maybe it is everywhere else. I don't, except in an analog clock. There are very few instances I can think where phase may seem to be an evident, where we can make an evident relation to a quantity like phase. Yes? So, we have to use some kind of interferometry, but yes, that is a good point. Where do we get the reference from for the interferometry?
We should use split the same beam twice, like an MZI.
Yeah, so now we are thinking, so you should think about this further and then come and figure out a method for doing the phase measurement, right. So, That is one we can say perspective. There is a second perspective to this problem, okay, that comes as follows. We will see soon in metrology the following thing, right. We measure something in one of the two domains, the spectral domain or the spatial domain. We get a signal, okay. So then it is quite possible that in certain scenarios we lose information about the spectral phase and end up measuring only the spectral amplitude. But still we want to know the spatial or temporal structure of the object of interest. It could be a pulse in time, it could also be like a structure of a crystal, for example, right. So then the problem that we are set up with is the following, in that in order to measure spatial or temporal structure, the problem that we have in hand eventually becomes a problem where we are struggling to retrieve the phase, retrieve the true phase profile. The message that this sort of an exercise gives us is, if I get a fairly accurate measure of the phase profile, through some method or through some process, then I have more or less gotten a very good idea of the problem. Amplitudes also could be are important. I am not saying no, it's not, it's utterly irrelevant. That's not really what it is. It is important, but an even more important thing is the phase profile. So if I have some information, like in X-ray crystallography, for example, we do something like this. X-rays are scattered from a sample, okay, whose structure needs to be determined, and what you essentially get would be dots of whatever, symmetry and so on and so forth. What you measure is spectral intensities in the reciprocal space. So, kx and ky are reciprocal vectors. Okay. So, of course, they have units of inverse of length. So, this we do a measurement in the reciprocal space, in the space of the diffracted beam. Now, it would be great if for each k we had an idea of the corresponding spectral phase, that is phi as a function of say kx, ky, kz. If we had this information, it would be great. We would have determined all crystal structure of DNA, RNA and everything much earlier, and one would have a full map of all proteins and all the stuff. Life would have become fairly easy. Maybe even the protein folding problem wouldn't have been as challenging to solve. I don't know, but that may be an overreach for me to say. But still, life would have been a lot simpler. We need to retrieve the phases from a pattern of intensities, let us say. But why we call that a phase retrieval? We get a feel for this because it seems in any form of recovery of signal, the phase information is primary, and in amplitude information, even you can admit maybe larger errors, or one can take that out, or one can basically peg the retrieval problem on phases rather than anything else. We will see this in our very soon in pulse measurement techniques, which is why I am making this point. Okay, very good.